We want stdlib to fulfill the role of a de facto standard library in JavaScript and on the web, namely a piece of software that is consistently tested, benchmarked, and documented, and that every developer can depend on.
This podcast episode features a discussion with Athan, the maintainer of stdlib, a JavaScript library designed for numerical and scientific computing. Athan shares his experience, his career journey, starting from a non-computer science background through his PhD program at Oxford and eventually leading to his passion for open source development. He explains the unique benefits and challenges of building scientific computing tools for the web, emphasizing the powerful capabilities of JavaScript when written correctly. Athan also discusses the importance of standardizing arrays, the evolution of web technologies, and the collaborative efforts required to make projects such as stdlib successful. This episode highlights industry use cases, potential applications, and the ongoing efforts to attract contributors and to fund open source initiatives. The Inspiring Computing podcast is where computing meets the real world. This podcast aims to trigger your curiosity by talking to proficient and advanced users of MATLAB, Python, and Julia, who use these tools to deepen their understanding of the world, simulate, explore trade-offs, and gain insights that help companies add more value. In addition to this, we will also be talking to product marketing, toolbox authors, package developers, and library maintainers to see what drives the development and what issues they're solving for others to benefit from. Athan, thank you very much for joining Inspiring Computing. Welcome to the show.
It's a pleasure to be here. Thank you for having me. I really appreciate it.
First of all, you work at a company called Quantsite, right? So I have utmost respect for the company. You guys seem to collect an amazing portfolio of cool people. But above and beyond the company you work for, you're the responsible and maintainer for this awesome package, stdlib.io, but not for 1 or 2 years. This thing has had over 10 years of work of your life has been into this. That's impressive out of the gate.
Yeah, it's been a long road, to say the least.
So it's actually a privilege to talk to someone who's gone through all the steps. So many people like creating open source projects, but very few think about, okay, what does that mean 15 years from now, what that means and what type of a person will I become? But before we get into that exactly, can you maybe tell me a little bit about your superhero origin story? So I think on your LinkedIn profile, I see that you've studied architecture, you've gone through maths, you've been in Oxford, you've been in multiple universities. Tell me, how did you land up on stdlib?
How long we got? I suppose I can start with the fact that I was born and raised in rural Missouri, which for the international listeners out there, and maybe even some folks in the U.S., is a state smack dab in the middle of the United States. And the way I typically characterize my origin story is as a biased random walk, a winding path in which I benefited from a number of rather lucky breaks. And instead of having a single overarching vision, I tended to have like mini visions and let my curiosity often get the better of me, finding myself deep down rabbit holes and getting knocked off far from my original path. So with this in mind, I'll start by saying that while I work in the technology space, as with many individuals having origins in the sciences, I have no formal CS background, except for maybe a single course in C++ during my undergraduate studies, which I pursued at a small liberal arts college called St. Peter's University, which is right across the river from Manhattan, New York. And when I think about my origin story, I think that the most formative period of my life is unquestionably the time that I spent in academia. Before university, I was very uninterested in anything having to do with academics. I never liked reading. I could barely hold a conversation if it didn't involve sports. In fact, my dream in life was to become a professional American football player and later become a football coach and commentator. However, once I got to college, I had something of an intellectual awakening, turning me into a voracious reader and spurring me to take full advantage of a liberal arts education, hopping around quite a bit from one discipline to another. I started off as a communications and secondary education major, and before dabbling in philosophy and architectural design, and then I moved on to physics and math. Toward the end of my undergraduate education, I worked on a couple of research projects related to math and biology and decided that my goal in life was no longer to become a football player or an architect, but to pursue a dual MD PhD degree and eventually become a medical doctor. However, by this point, I was due to graduate, and in order to pursue a medical degree, I needed to take some prerequisite courses in chemistry, which I hadn't completed during my undergrad. So I headed back close to home to Missouri, and there I pursued a post-baccalaureate certificate in pre-medical studies at Washington University in St. Louis, also commonly known as WashU, where I took courses in physical and organic chemistry, biochemistry, medical anthropology, and anatomy. And as a quick aside, if you've never had the pleasure of dissecting cats and smelling like formaldehyde for days on end, lucky you, but I digress. But while at WashU, I was reapplying for the Rhodes Scholarship, a fairly prestigious scholarship for which I had been a finalist the year before, in order to study at the University of Oxford, which is based in the UK. And I reached out to a PI and the head of a research lab there, whose work I had come across during previous research stints, in the hopes that by expressing interest in joining his lab, he might be able to pull some strings, give me a ringing endorsement, and hopefully boost my chance to get in the scholarship. I'll embellish here and just say that he seemed to think this was a brilliant idea, and also suggested that I apply for another fellowship, a UK-based fellowship called the Clarendon Fellowship. And while I didn't get the Rhodes, I did get the Clarendon. So soon after I finished up at WashU, I was packing my bags to pursue a PhD in biological physics at Oxford. And when I arrived at Oxford, I started out as a wet lab scientist, meaning I was spending a lot of time in a dark room, mixing reagents and conducting experiments. My research area was the biological process of transcription. And for those listeners who aren't familiar, this is the process of transcribing your DNA to RNA before being sent off to proteins called ribosomes, which use that RNA to synthesize proteins. And without going too far into the weeds, this process of transcription is performed by a protein called RNA polymerase. And I was studying the initial steps of transcription, in which RNA polymerase binds the DNA, splits the two complementary DNA strands, creating something referred to as a transcription bubble, and then proceeds to generate small abortive RNA strands. And what's interesting about this process is that we were studying this phenomenon at the molecular scale in real time. And we're using a technique called Forrester resonance energy transfer, in which two dyes probabilistically emit light of varying color, depending on how physically close they are in space. And by measuring the ratio of, say, green light to red light, you can infer physical distances, such as when a protein is open or it's closed, or when a DNA strand has been pulled apart. And we were doing this circa 2008, and the data that we were collecting was in the form of images which looked very much like star field data, as might be gathering by imaging the brightness of stars in the night sky. And to analyze this data, we needed to write software. And as I mentioned earlier, as I'm prone to letting my curiosity get the better of me and going down rabbit holes, I soon bored of spending late nights in the lab and grew very interested in writing software for data visualization and analysis. And in terms of becoming a software developer, I suppose the rest is history. From that point on, I spent the rest of my PhD and thereafter toiling away at a computer, learning how to code without formal education, by failing and making a lot of mistakes.
Was that the first time you actually started programming?
Pretty much, yes. Yeah. Not much has changed since that time. I found something extremely captivating about writing software, never ceasing to find new programming puzzles or to solve or challenges to address. And there's always been something there to learn and to scratch my intellectual itch. And I suppose if you were to frame it in terms of psychology, when you're a programmer and you're working a lot in code, you're getting a lot of intermittent rewards. And intermittent rewards are like the path to addiction. And so that was definitely the case for me.
Wow. Okay. So how did stdlib come into the picture? What is this and why is it so important?
The official project description is that stdlib is a standard library for JavaScript and TypeScript with an emphasis on numerical and scientific computing applications. For those coming from the scientific Python ecosystem, the easiest way to think about stdlib is NumPy and SciPy, but written for the web using web native technologies. Of course, someone might hear that and say, okay, why didn't you just call the project num.js or sci.js or something more obviously conveying its numerical focus? And the reason is that we simply believe our mandate extends beyond the obviously numerical, and we wanted to provide a library which effectively established the standard for performing common everyday operations, meaning we want stdlib to fulfill the role of a de facto standard library in JavaScript and on the web, namely a piece of software that is consistently tested, benchmarked, and documented, and that every developer can depend on, whether it's for manipulating the characters of a string, or operating on complex numbers, or performing asynchronous tasks, or working with multidimensional arrays. And while JavaScript has been growing its standard library as of late, this wasn't always the case. Historically, JavaScript's standard library was small, and there were numerous utility libraries out there that were written by users in the community. And this small core philosophy had both benefits and drawbacks. The benefit was intense ecosystem or competition, resulting in a lot of experimental designs and innovation. The drawback was and still is significant ecosystem fragmentation. Every project seemed to have its own way of doing things, different kind of like idioms and conventions. Each time you wanted to perform a task, you'd have to search for the exact package doing what you wanted, evaluate the alternatives, and then learn the unique way that package author did things. And we saw this and we said, okay, our interest is in writing numerical software, but in order to do so, we're going to need to fill in a lot of the gaps. And we weren't willing to depend on a bunch of third-party software. So we decided that anything we needed, we were going to implement in-house according to our way of doing things, up to our standards, and in such a way that every bit of code and documentation has a single voice and reads as if written by a single author. And eventually, as we anticipated, our stable functionality continued to grow beyond just numerical and scientific routines to include a considerable amount of functionality you'd want and expect from a comprehensive standard library. And with this in mind, I suppose another way of thinking about standardlib and what it aims to be is that just like Julia and MATLAB are programming languages with a numerical focus, while still offering general utilities, we want standardlib to provide the same level of comprehensive functionality as those environments. Of course, the main difference being that Julia and MATLAB also encompass like the language and the language's execution, whereas with standardlib, we can delegate the runtime to dedicated JavaScript engines and focus solely on that end user functionality and really provide that kind of comprehensive set of tools that people can use as a substrate for not just building numerical applications like you would with NumPy or SciPy, but any kind of like general purpose compute intensive application.
Did you run into this idea of the web as the solution for mathematical computing, or where did it come from? I'm curious.
Yeah, I guess there's probably a bit more details there, which is that I think toward the end of my PhD and a little bit after, I was working for a tech education company in London where I was like running workshops and building out curriculum for data visualization analytics. And this was around the time of the big data craze when Hadoop was becoming a household name. And at some point I realized I wanted to move back to the US and I wanted to be where the action was, and that was Silicon Valley. I knew I wanted to work for a startup and ended up being I was recruited on AngelList by a small startup called Node Prime, which was based in San Francisco. And so with a job in hand, I moved back to the US and worked for that company for a year and a half before the company started to implode. And it was while I was at Node Prime that I became much more heavily involved in open source. I then joined like another startup called Verb, which was also based in San Francisco. And I left that company because I realized that what I really wanted to be doing was working on open source. I already had dreams of establishing a foundation for scientific computing on the web, and I wanted to devote myself fully to that cause. So for the next 2.5 years, I could rain down my savings and work full-time in open source, occasionally receiving some crowdfunding and traveling to speak at conferences. And it was during that time that I was at Node Prime, and then thereafter I was laying the seeds and building a lot of the foundational stuff which would eventually become standardlib.
So did I understand correctly that you took 2 years of your life and you said, okay, I'm going to do full-time open source, and actually it doesn't matter if no one pays me, I just want to do this out of passion? So tell me, how do you get to that stage? Is this a place of like you're super angry with the commercial world, or are you saying that no, actually open source is just the way to make the world better? How does somebody in his late 20s make that call to say, okay, I'm going to give this a shot, no income, just out of pure pleasure? This is a special move. Not many people have the courage to do that.
Yeah, I should state that I was in a very privileged position to be able to do this. One is that after Node Prime ended up being bought by Ericsson, and I had a little bit of equity in the company. So I had enough to float me for a year on that. And I had enough savings built up that I could take the leap. But really, it was to scratch this intellectual itch. And I suppose to your question of what got me explicitly started on standardlib, which was that for me, the genesis kind of goes back to my PhD at Oxford. And toward the end of my PhD, I had gotten into web development and grown disillusioned with MATLAB. Around this time, D3, a popular JavaScript library for authoring data visualizations released, I saw this and immediately started envisioning what it would be like to rewrite everything I had done in MATLAB in JavaScript and as a web application. I had spent enough time fiddling with Java Swing to build UIs in MATLAB that once I experienced writing UIs in JavaScript and with web technologies, I never wanted to look back. Fast forwarding a little bit to when I joined that startup in San Francisco after completing my PhD. When I joined that startup as a data scientist, it was a full stack Node.js shop, and which was working on a product for data center infrastructure analytics. And the idea was to deploy software to racks of servers, collect data such as CPU, memory, and disk utilization, and then perform analytics to detect anomalous activity, predict failures, and understand network topology. And as I worked on building some of the initial dashboards, I realized that the time series we were collecting from these servers looked a lot like the noisy time series I analyzed during my PhD, where I had implemented and applied various machine learning and change point detection algorithms to detect anomalies and monitor state changes. So I had the idea during that time to start porting the software I had in MATLAB to JavaScript. And of course, this meant I needed to re-implement MATLAB's basic matrix and vector primitives, operators, and kind of transformation utilities. And slowly but surely, I built up a library of various utilities, which I subsequently open sourced. And this was really the true rudimentary basis for what would eventually become standardlib. And when I was at Verb, at that second company, I was basically spending all my nights and weekends working on this project. And it was just the case that I was just checking in and checking out when I was going to work. And I was like, I can't do this. What I really wanted to be doing is I wanted to be home on my computer, trying to really push us forward. And I decided to take that leap to work on open source full time.
So there's lots of things here to dive into. First thing is, typically my listeners are either from the MATLAB ecosystem, Python ecosystem, and Julia system, but you've mentioned the word JavaScript. So enlighten me, why did you not go down, I don't know, the NumPy or the Julia, or I can understand that maybe you had your internal frustrations with MathWorks or MATLAB. Walk me down this thought process of, okay, it can't be done like that and it has to go to JavaScript, which intuitively is not, maybe today it's a bit easy to make that call, but we're talking about 14, 15 years ago or something. How did you think about this? Why JavaScript and not, I don't know, C, C++, or just jumping on Python? Because I think that's when NumPy was beginning to emerge.
Yeah, NumPy was certainly taking off around that time. We're talking about like 2010, so that's right in that rise where people were really warming up to Python at the time. I would say that it was certainly the case that I dabbled in the scientific Python ecosystem during that time. In fact, I'd flirted with the idea of, even during my PhD, of using Python instead of MATLAB for writing a lot of the analytics software that I was developing. However, there was just something specifically about the web, about building a web application that wasn't dependent on any kind of complex build and server architecture or requirements that I found particularly alluring about the possibilities of what could be possible. The fact that you could build a web application, send that to a client machine, and basically take full advantage of the computing capabilities of that device to run certain analysis without needing to have very complex backend server architecture. There was just something different that I recognized you couldn't do with those existing languages and ecosystems, and they just really weren't built and considered and designed with the web as a primary audience for what they were doing. And so I knew that you had to do something like different. And I also recognized that there were certain advantages to building something which spoke the language of the web. That every device more or less has a web browser, and there's a highly optimized execution engine there that you could take advantage of to get effectively near native speed. So there was no existing solution that could really allow me to take advantage of the full capabilities of the web, which already had built-in hardware integration. Like HTML5 had just been the dominant thing. You saw a proliferation of access to different device capabilities, like the gyroscope, the accelerometer, to camera. You already had built-in capabilities. You didn't have to go write independent drivers yourself. All these browser makers were doing it for you. If you could take advantage of this incredibly powerful platform and leverage these capabilities, you could do some really interesting things. But the reality is that there wasn't, because JavaScript was often derided and it wasn't really considered a serious computing language, no one had really invested the time and effort to try to build a lot of the capabilities for scientific computation on the web. Well, low-level numerics, et cetera. It was just like a toy language that maybe you spin up a pop-up. There just wasn't, at the time, there wasn't really any solutions that satisfied my needs and my vision for what was possible.
So in the last few years, there's been a bit of a push, at least in the Python ecosystem, to get Python running on the web, right? So a way is with Pyodide, right? And then you get it working through WASM and then the WebAssembly, and there's a subset of things that work, and then all the core maintainers and libraries try to make sure that their stuff fits in there, which many people don't realize the amount of effort it goes into making that a reality. And the intent is just to see it, have Python running in a browser, right? So the way you just articulated it, that you saw this something like a decade before anybody else. So can you quickly, just for my mental model, what are the pluses and deltas, if you will, of going down the route that you did versus what it feels like a large percentage of the Python ecosystem is investing in today through the WASM and the Pyodide route?
Yeah, so WebAssembly it's a portable compilation target. It basically provides a binary format for execution on the web, and it historically allows for statically compiled languages such as C++, Go, Rust to compile to a compilation target that web execution engines can interpret and then run, and you can get near native speed. And where WebAssembly really excels is where you have an entire application that you've written in some other language and you want to deploy that and you want to press go and it runs. That model is perfectly fine, especially if you're doing analysis and you've maybe got your Jupyter notebook and you want to share that notebook with a broader audience. So you see this particular avenue, this particular technological choice as being an avenue for the dissemination and communication of your research results. And in those circumstances, the constraints and kind of performance profile of what you're trying to achieve is very different than what you're trying to achieve if you're trying to build a web application that is maybe going to power an e-commerce site, or it's going to provide a CRM, or it's going to provide something else on the web, where low latency and small binary sizes or application size or bundle sizes is like an imperative because of the cost of not only shipping that from your servers, but also from the performance cost of downloading that onto edge devices, which may be resource constrained or might have low network capabilities. A lot of the focus that's being put into the Python and R ecosystems, like there's Pyodide with Python, there's also WebR and the R ecosystems, and all that's like great. And that really allows for people to create like interactive web apps, etc. But the reality is that you have to, in order to execute that Python or R, you need to ship down an entire interpreter that's going to take that Python, translate it to WebAssembly, and then execute it to WebAssembly. And that's a pretty significant cost. Like when you load Pyodide in a web browser, it takes, I think, around like 4 seconds. And then when you start layering on like NumPy and SciPy, these very large monolithic libraries, you're shipping megabytes of code that may never be executed or needed within a web application. It's a bit different when you approach the problem the other way from a web application perspective, because at that point, what you're really trying to do is you're trying to build, you want to atomize all the different functionalities such that end users can independently consume and remix and combine all these bits of functionality without any of the cruft that comes with these large monolithic libraries. So if you're using NumPy, you might use some of it's like vectorized functionality. Maybe you want to evaluate the sign function over an array of values. In the server context, fine. You download all of NumPy, you use a single function, you call it a day. But if you were to do that in the web context, where you only need a single function, there's a lot of it. It's crazy. You wouldn't want to do that. And you need to fundamentally architect your library in a much different way if you want to really address the needs and constraints of the web platform and how web developers are needing to build applications, especially when they're trying to address a wide audience of people who may not have all the compute resources of the network capabilities that you have at home on your server.
I see there's an added value. So the JavaScript world, indeed, it's much more streamlined. But it's also not known for pure performance. But maybe you might argue, okay, do most people understand the impact of how fast sign is in C versus JavaScript? Maybe that's not such a big problem. But I think where a lot of at least on the technical computing side, there was a lot of the linear algebra and bringing mathematics into the JavaScript world. This is not a small feat, right? So anyone who's worked in scientific computing, you're standing on the shoulders of giants with the Laplace and the Blast, and it's like, let's not touch that stuff. Let's not rewrite that. Let's use it because there's been tons of effort going there. So how did you think about, okay, I'm going to slowly but surely peel away the layers of the onion and implement function by function and, I don't know, probability distribution? And you probably said, okay, look what the world did. And, oh, MATLAB, they started with an array. Okay, that seems like a solid place. How do I start doing matrix multiplications? And you say, well, how hard can it be? Well, anyone who's gone down that rabbit hole very quickly says, yeah, this is a lot of work. What was that experience like? Is that how you started? Did you start off thinking just like sign, or do you think of arrays? Did you architecture this to be a bit based on a specific array format, or how did you go about this back in the day?
It was a very ad hoc thing. When I was at No Prime, it was, all right, I need to implement these various algorithms for doing change point detection or dimensionality reduction. What were all the different functionality that I used in MATLAB, and then I just started implementing that and trying to mimic those APIs as much as possible. And
okay,
I wouldn't say that I was doing anything super sophisticated. Often there were just naive implementations. But yeah, often I was just like looking at what prior art there was and trying to stitch together implementations in JavaScript in a very piecemeal fashion. And then over time, that collection grew, and you have a sporadic collection of, I don't know, some statistical distribution stuff. You have some low-level numerics. You have like scalar kernels. And so at some point, stepped back and said, okay, need to be a bit more systematic and holistic about this. Like, what are the kind of like constituent parts that we're going to need to replicate a lot of the functionality that you see in these other environments? And so I spent a lot of time like reading NumPy code and understanding how they do their universal function architecture and vectorization techniques. And I was like, all right, let me go ahead and implement that in JavaScript and see how far I can get. And similarly with Blast and LAPACK, the dirty secret is most of these programming languages, Julia, R, NumPy, et cetera, are just fancy wrappers around these Fortran libraries that people have always used. But again, at some point we recognize that there's a fundamental limitation. You aren't going to be able to just ship all of LAPACK to a web browser and a web application because it's just too high of a cost. So you need to break that out. And we started bit by bit re-implementing Blast routines, et cetera, in JavaScript, but also in Node.js environments, hardware optimized bindings to hardware optimized libraries, and having vanilla C implementations for compilation of WebAssembly. And so it just grew bit by bit. And each time we grew the library, the scope of what was possible expanded.
It's impressive because in the Julia ecosystem, that's one of the things, right? When you want to compile some Julia binary, as soon as you do some mathematics, it's hard to just tear apart the single part you need. And then, okay, so now the Julia ecosystem has got a bit of an issue. How do we minimize the binary? So you've jumped the gun by 10, 15 years of slowly but surely taking step by step. But I'm curious that how do you find people who are willing to do this? So how do you inspire someone to tackle this problem? Was this you by yourself, and then maybe you had a friend, and then 5 years later, another person, and then it becomes super popular to where it is today with, I don't know, your 5K stars on GitHub? Or tell me a bit about the journey of you being a single person with this idea, working 2 years, slowly but surely, and then all of a sudden you've got this wild crew of people supporting you on a daily basis. You're doing pull requests and helping you out implement some of the hardest things on the technical computing front.
Yeah, we need to zoom back a little bit to, I think when I was working on this, it was like in 2013, Node.js was really starting to take off. And it was, the Node.js community was much different back then than it is now. It was comprised of like hackers and hobbyists and systems programmers and people that were interested in distributed peer-to-peer computing and blockchains. It was just like a very interesting time. And I wasn't the only one thinking about this problem and trying to innovate in this space. There were other people that were building out little numerical libraries and experimenting with what it would mean to do scientific computing on the web. So during that time, I connected with a few of them. And one of them was a guy by the name of Philip Burkhart. He was a graduate student at Carnegie Mellon at the time. And he was interested in using JavaScript for doing various statistical functionality. And so we connected, and then we started a collaboration, and we started working on a lot more of the rudimentary parts of the standardlib project. And he was working on this as part of building an e-learning platform, which I can talk about as well. But the real thrust of all the scientific or all the statistical computing stuff, he just started building all the hypothesis testing, the distributions, the random number generators, et cetera. He had a need, and so he started building it. And that kind of formed the foundation of our collaboration, which has lasted till the present day. He and I still collaborate quite heavily on this project and basically talk every week. And then, in terms of like, how have we been able to get more contributors? It's been a very slow and arduous process. I think there's definitely a bit of survivorship bias here. We're just the last project standing in some senses, but it's been a grind. It's been a grind to find people and to upskill them and to get them to the point where they can really contribute. I think if I think back and if I have the benefit of hindsight, we definitely had a contributor pipeline problem for several years. We spent a lot of time and energy presenting at conferences, promoting updates on social media, and trying to leverage things like Stack Overflow's open source ads program in order to raise the project's profile and attract contributors. We'd go and we'd highlight development efforts, maybe show a demo or two, run a workshop, and then have the inevitable call to action to come contribute. But this really didn't move the needle. We'd just get like a small bump in stars, maybe some shout outs on Twitter and maybe a PR or two, but the project just wasn't sticky. And if I had to answer why these efforts didn't move the needle, I think it was probably twofold. One is that if you look at some of the most successful open source projects today, your NumPys, your Julias, your PyTorches, Drupals, you name it, projects at the long tail of the open source distribution, those projects have managed to become critical dependencies of businesses worldwide. And by becoming critical dependencies at the top level of the stack, not somewhere buried deep in the dependency chain, but very visibly at the top, companies have become more and more willing to pay their employees and others to work on them. And by paying developers to work on them, you jumpstart and build community. And an open source project becomes a place where you can network, you can learn from subject matter experts and build your brand by working on a high profile project. And the reality was that standardlib, for a lot of its existence, was not such a project. We hadn't become a critical business dependency, at least not in a holistic sense, where we were providing a wide-reaching and very visible foundational infrastructure. So without industry buy-in, we were very reliant on volunteers, people just casually dropping by and dipping their toes in the water. And I think this brings me to the second reason I think our efforts didn't really move the needle, is that our sample of volunteer contributors and the conferences at which we were presenting didn't have the right cross-section of skill sets and needs. And of course, as you highlighted, in order to build a foundational library for scientific computing, we needed developers with expertise and experience and interest in writing numerical algorithms and writing them well. And in the web community, there just aren't too many of those. Anytime we presented, our pitch was fairly niche. It was about an emerging use case, about all the possibilities of scientific computing. And while interesting, the majority of individuals hearing our message were building web apps and deploying web servers. And all the people doing scientific computing were over at SciPy and JuliaCon and other technical conferences. And those conferences weren't really interested in what we had to say because we were writing things in JavaScript. And if there's one programming which people love to hate on, discredit, and misrepresent, that language is JavaScript. Right. So after banging our head against the wall and continuing to plod away, we said that, okay, maybe what we need to do is we need to reorient our contributor funnel to people who are just starting out and eager to learn. And in short, we decided we needed to really invest considerable time and energy to train and mentor in order to effectively create the contributors that we needed. And the perfect avenue for doing this was through the Google Summer of Code, or GSOC program, in which individuals new to open source, often college students, apply to be paired with mentors and maintainers from open source projects. And importantly, as part of this program, Google provides contributor stipends, which means that projects effectively have contributors working close to full time for 3 months over the summer. And last year was the first year in which we were finally accepted into the program, and the interest in standardlib as a project was overwhelming. And because competition was so fierce, we were able to be quite selective about who we thought could be a good fit and had the skills and aptitude to quickly upskill in the project and ultimately be successful. And eventually we ended up with 4 GSOC interns. But even then, several of the folks who were not accepted ended up sticking around. So in short,
really?
by reorienting our funnel, we were able to significantly expand our contributor base and help individuals grow into becoming maintainers. And once we built this kind of momentum, we really started investing in community activities, such as having weekly office hours, and then for especially promising contributors, almost doing recruiting efforts where I would make an effort to directly set up one-on-one calls, thank them, provide a high-touch opportunity for them to ask questions, and hopefully align their interests with standardlib priorities. And that's just fed into itself and created some self-sustaining momentum. So it's just been a very long process of perseverance and resilience.
This project sounds super interesting. It's got lots of stars on GitHub, so that must mean there are tons of people using it. So congratulations. But can you walk me through exactly who actually is using this? Do you have key examples that come to mind?
Yeah, so I think in general, when we think about the types of applications that this could empower, when you think about building a scientific computing library for the web, I think there are 3 key benefits around privacy, security, and low latency. And to help illustrate this, recently I was talking to a medical researcher who wanted to deploy analysis software, which would allow users to upload their private data to a web app, perform some image analysis on that data, and then allow them to see results without ever having to send any of that data to remote servers. And that's a pretty powerful concept because it enhances privacy and security of potentially very sensitive information. And we're starting to see this, especially with these large language models, where in other deep learning type machine learning, is that you can deploy a model to the edge and allow people to do like localized computation without ever needing to touch in the data that model is being used to analyze. And so there's a lot there in terms of privacy and security, but there's also the benefit of very low latency. Another example of this, a few years ago, Nature did a special issue on Jupyter, and they worked with Rackspace to provide like a hosted solution, which would allow Nature visitors to interact with Jupyter notebooks. And you can read some of the blog posts. This required like considerable engineering effort, the spinning up and spinning down of servers, and a very non-trivial amount of infrastructure. And around this time, Philip, my collaborator with standardlib, he was at Carnegie Mellon. He was building this online learning platform for statistics and data science. And if he had used that Jupyter approach for every student in an online laboratory, he would need to spin up new backend kernels. He might need to dynamically spin up new servers, do some load balancing, and manage a fairly complex infrastructure. And by implementing much of the statistical functionality and data science algorithms that he was interested in teaching directly in standardlib and in JavaScript, he was able to execute all that functionality directly on student web browsers, which meant he only needed a single server to send a web application with some additional JavaScript. And from that point on, all computation, data processing, statistical modeling happens solely on the student's machine without any complicated install or build process. And this is precisely the benefit of client-side web computation, where you can push computation to the edge of the network, leveraging effectively the supercomputers that everyone has in their pocket and many people have sitting on their desk at home. Now, in terms of a couple places that kind of come to mind that I hadn't really expected to see adoption of standardlib and really highlighting the use case for what we've been building, is the first that comes to mind is that Oracle has a product called NetSuite, which is an enterprise resource planning software. I don't know exactly what that is, but some enterprise thing. And as part of NetSuite, they have a scripting language called SweetScript, which as far as I can tell is compatible with JavaScript. And in this particular case, they promoted and showcased standardlib in a way which really aligns with that idea of being a comprehensive standard library, which beyond its numerical capabilities provides a wealth of really well-tested and consistently documented functionality, and also helps address that ecosystem fragmentation problem by providing like a one-stop place that you can go without needing to go off and sift through thousands of different packages. And the second place that I find really interesting is as an extension to Google Sheets. So in order to allow developers to extend the capabilities of the Google Suite, Google provides a JavaScript SDK and a language called AppScript, which is just JavaScript with some specialized global variables and build constraints. And the cool thing about this SDK is that extensions can expose new commands in Google Sheets, which look and feel like normal Excel commands that you enter in the formula toolbar, but which are implemented and executed in JavaScript on the back end. And this means that a good chunk of the functionality in standardlib, from machine learning to linear algebra to advanced statistics and string manipulation, can be exposed directly in Google Sheets in a way which most spreadsheet users are already familiar with, without needing to introduce a new language or set of calling conventions. And what's also cool is that Excel provides a similar extension functionality also in JavaScript, meaning that the two most heavily used pieces of spreadsheet software have elevated JavaScript to like a privileged status when authoring extensions. And while I at least always had in the back of my mind that a JavaScript-based client-side spreadsheet application would be a great use case for standardlib, it turns out that two of the most widely used pieces of software provide a built-in way for potentially shipping standardlib and getting standardlib into the hands of millions of users. I didn't have that on my bingo card, but I certainly find this possibility really exciting.
So when I stumbled across it maybe a couple of years ago, I thought, oh, this is a wicked successful project. This is really great. And but you often take for granted that to get to that stage, there was years of maybe not so many successful evenings in one way. But I have to say that maybe there's also a timing element. So even like MATLAB, they've also got the MATLAB Online. So they've shifted the whole ecosystem. And you saw 15 years ago the 3JS library. That was wicked fast, right? At the time, the visualizations were actually outperforming anything else out there. It was just a super painful thing to use. But once you got your head around it, I was like, actually, this outperforms all plotting graph engines out there.
Yeah.
So I can see some part in hindsight is, if you can do the graphics so quickly, then the numerics has to follow. Why do we need to split the two worlds? Let's keep them together. So I can
exactly.
I can see that happens, and I know from the MathWorks side, if you follow this, they've had generations of changing the plotting ecosystems to move to the web, and that's not an easy thing to move that legacy code or mammoth, rewrite it. And the Python ecosystem, the same thing, right? So you get the variations. Do you depend on the JavaScript role? Do you build it from scratch? And there's the two different mainstreams, and it feels like everyone's gluing stuff together. But you said, why can't we just? Why do we need to glue stuff together?
Exactly. That's precisely the idea. And especially when I was building kind of the dashboards at Node Prime, when I was doing that data center infrastructure analytics, it was definitely the case we were getting such large data sets that we needed to downsample the data, and we needed to do that very quickly, cross-filtering, et cetera. And if we were constantly making server calls to do this downsampling and some of the rudimentary analytics, it would be very slow. And it was definitely the case of there's a light bulb that went off that said, why don't we just marry the computation and the rendering engine and have those things be very intimately connected? And so, there was definitely an element of timing. It was riding that zeitgeist at the moment where there was a lot of interest, and Node.js did a lot to legitimize JavaScript as a general purpose computing language. Before that, it wasn't really the case. People had toyed around with server-based JavaScript frameworks, but Node.js was a turning point. And because of the influx of interest and all the different ways that people were experimenting and innovating at that time within the ecosystem, it just made it ripe as an opportunity to start exploring what scientific computing might look like.
But it's interesting. So when I look at this, when I think of it as a broad scale, it feels like the MATLAB, maybe the NumPy, the technical computing on Python, Julia, R, that they focused first on the maths, and then the visualization came after the fact, and then they realized, okay, the world's changed, so we now need to go to the web, and then there's an effort. So it became like the web became an afterthought, whereas JavaScript was the other way around. But on the other hand, part of that journey was like the exploration, so the REPL, was like this super cool thing. And I think MATLAB came up quickly. The Python was nice, and the Julia ones went up, and it's like this.
Yeah.
Any technical person likes the REPL, right? The REPL is a beautiful thing. And then when you go to the JavaScript world, it's like, maybe I'm speaking out of turn without much knowledge. It feels like that was the afterthought. It was like, yeah, okay, now everyone else has got this REPL. We got to do something as well. Is that a fair assessment, or am I looking at this from a very naive perspective? And maybe how did that actually impact you and your project? Because I'd have to believe technical computing people, they tend to like that REPL. That's a big deal.
Yeah. The one thing I really appreciated about MATLAB was that kind of interactive development workspace where you could see and inspect variables, and you had to plot in the window, and then you had your main REPL, and then I would go back and forth with scripting. And you're right, like the web in general didn't really have that. Your REPL was that you had to open up your developer console on your browser, and you might start entering in various random commands. But it's not the same experience. And I think Node.js changed that because it provided a server-side framework. It had a REPL. And I remember there were a lot of people during that time like they were building out CLI utilities, and they were using the REPL to provide like workshoppers, and it introduced this huge ecosystem of web developers to the REPL. And we then piggybacked on that, identifying that, yeah, you needed a REPL for doing interactive data exploration, et cetera. And so we built our own that wrapped and exposed a lot of the stdlib functionality so that people could have an experience similar to IPython. That's still been an ongoing thing that we've been working on to this day, is trying to provide a really solid REPL experience for doing interactive data analysis.
So you make it sound like this is an easy thing. The REPLs are by no means an easy task to reproduce and get going. You take it for granted, but there's tons of work in there.
There's a lot of work. But as with many of these things, when you think about your Julias and your MATLABs, not only do they have a wealth of functionality, but they also have a runtime, there's like a language spec, et cetera. Those projects are much bigger. For us, we were able to stand, as you mentioned, on the shoulders of giants. So we could take advantage, we could outsource all the execution, et cetera, to the JavaScript engines. For the REPL, we were able to stand on the shoulders of all the Node.js developers who built out the fundamental infrastructure for building out REPLs. And so we were able to borrow those ideas and then just start hacking away and making our own. And so same thing with all the linear algebra functionality. If we had to implement all these things from scratch, we'd be dead in the water. But because so much prior art exists, we can pick and choose what we like and borrow ideas and be much further along than if we had to do all these things from scratch. And that's the beauty of open source, is that you can learn and borrow from others.
So learning and borrowing from others. So in the technical computing world, a key component is these arrays, right? How do you define an array? I know some of your fellow colleagues at Quantside have played a role in standardizing arrays, and I'm assuming you played a role here. So what was your role? Does your stdlib follow suit, and does it follow the n arrays that the NumPy is pulled together? Did you contribute in standardizing what arrays should be defined so that the JavaScript ecosystem plays along nicely, or do you have your own implementation that makes it better, faster, based on JavaScript's internal workings?
Yeah, it's a mixture of both. When I think back, I should also just say this. At Quantsite, part of my day job is working in the scientific Python ecosystem. And one of the projects in which I'm involved is the Consortium for Python Data API Standards, which was an initiative led by Quantsite to bring the key stakeholders across the scientific Python ecosystem, like your array libraries such as TensorFlow, PyTorch, JAX, Dask, you name it, and then some of the downstream libraries, get them in a single room and try to address like the ecosystem fragmentation problem. Because what you saw across the Python ecosystem was a increasing fragmentation where array libraries more or less shared the same APIs, but diverged in little annoying ways. And so downstream libraries would have to have specialized code paths to handle this particular array library and this other particular library. And what you end up getting was people just throwing their hands up in the air and just going, I'm just going to focus on one array library. I'll build on NumPy. I'll build on PyTorch. I'll build on JAX. And you have these siloed verticals. And Quantsite, when I joined, which was back in, I think, 2019, saw this problem and said, we need to do something about this. And the solution that they said was, okay, we need to create a standard for arrays and tensors in Python. And what that means is that if you are working with a NumPy array and you have CPU-based computation and you want to eventually use GPUs, maybe via PyTorch, the ideal world is that you just have to switch out an import statement, and you don't have to have any of that bespoke code to say, oh, if this is a NumPy array, do this. If this is a PyTorch array, do this. And so by getting those people into a room and then standardizing some of the APIs and behavioral semantics, the idea is that you could have interoperability between these different array libraries. And that was one of the things I hoped to achieve by joining Quansight. In fact, when I think back why I joined Quansight, one, at the time I needed a job and I was running out of runway. And so I had started looking. I think maybe I'll go work at Google, or I'll do something else that was hopefully in the numerical computing space. And one day I just happened to see a tweet when I was scrolling Twitter from a developer at Quansight looking for someone with some JavaScript and numerical expertise. And when I looked at the company, I saw that Travis Oliphant, who's the creator of NumPy and SciPy, worked at Quansight. And so I was like, oh, this is interesting. And so one of my main motivations for pursuing the opportunity at Quansight was to learn from those closest to in the scientific Python ecosystem so that I could spy on the enemy, so to speak, and apply any lessons learned to actually building a library for scientific computing on the web. The web was always my focus. And I ended up staying at Quansight because I ended up learning so much. I could learn from all these different ecosystems. And so I could borrow a lot of the ideas from array and tensor computing in that world to developing the fundamental data structures in JavaScript, also recognizing some of the unique constraints about API design and taking advantage of certain compiler optimizations that browsers are capable of, et cetera, and catering and tailoring to the unique flavor of JavaScript. So yeah, it was a mixture of both, of where I was like borrowing ideas and learning a lot, especially in my work at Quansight as part of the consortium. And then also recognizing like, all right, how would you do this if you wanted to build for the web and you wanted to be able to decompose and allow people to mix and match functionality, swap out the dispatcher for another dispatcher, have some new backend. And so that required me to think about myself and others to think about like, how would we do things a bit differently?
So you make it sound simple, but actually it's a very fundamental thing that you just described, which I think many open source projects fail because they typically start, you've got this itch. There's this super smart person in the planet. They've got a little problem and they say, I want to solve this. They look around, I can't see it. And then somehow it gains popularity. And then it becomes very almost unavoidable that these silos appear, right? They build communities. You can look at it on the web framework, whether it's Django or FastAPI, these are big mammoth communities. But effectively, they're doing very similar things, right? I should be careful when I say that, but it's not that it's super different. But these communities grow, and then it becomes super duper difficult to align, right? It's really difficult to do align. But when you do align, there's a bit of magic. And I think you could draw the analogy with companies. They kind of start, they separate, they become silos, and as companies get bigger and bigger, then they try to centralize things, and then they decentralize. This idea of expanding and coming back together is a much needed thing, and being able to recognize that is super important. And I think to press the fact that you try to actively help in the Python ecosystem and that you make sure that you didn't forget about the web. So that itself, bringing a whole new language is nice because people get very religious almost about their ecosystem, and the other people are evil because they don't create the same thing or think the same way, and you're bringing these communities together. That's actually an example almost for society. So I'm glad that you did that. But I'm curious of how hard was that? Was that an easy trajectory? And I think there's still ongoing activities, right? This is a moving target which hasn't quite landed to perfection. Or am I mistaken?
No, it's definitely a bit of a moving target. Yeah, there's always I would say, you're always having to kind of like fight the forces of fragmentation. Speaking specifically about the Python ecosystem and other things, I mean, you're always going to have like diverging paths, and you have to actively fight to bring those things back together. And that's why these standardization efforts are so important. And technically, you're right. Like, setting aside all of the complexity associated with targeting different hardware backends and accelerators and maybe computational ways like graph-based optimization, that kind of stuff. Like, getting ecosystem alignment is a challenging social problem. And something you have to invest considerable time, because you're working with projects which often have a long history, are constrained by backward compatibility constraints, and have limited maintainer bandwidth. So it takes a fair amount of cajoling, arm twisting sometimes, and like some sweat equity to get projects to agree to change and make meaningful progress. But I think what's been really key in the consortium efforts when dabbling in the Python ecosystem is really like landing like kind of the key initial wins and really showing the potential of what happens when you do get ecosystem alignment. Because when we started seeing alignment among array libraries such as NumPy and PyTorch, developers and SciPy and scikit-learn started playing around and seeing, okay, now that we have a unified API, what happens if we design or go back and re-implement some of our things with that in mind, where we have a kind of like agnostic way of calling particular API conventions with certain expected output? What are the performance benefits? And we ended up publishing a paper in this in the SciPy, the journal associated with the SciPy conference, in which we showed some of the benefits of what happens when that's possible, where you can get 40 to 100x speedups just by swapping in one array library for the other. And so that was a light bulb in which people go, oh, if we actually adhere to this standard, we could unlock certain performance benefits. And array libraries also realized that this was their avenue for getting access to a much broader user and developer community, because PyTorch historically didn't have access or couldn't run in SciPy. But now we're getting to the point where you can do that. And that's pretty powerful, because it no longer do you need to reinvent the wheel. You can leverage all the hard work of these other open source communities.
So it seems like conceptually it makes a lot of sense, but the realization in doing that is a difficult thing. So do you have any, I don't know, lessons learned along the way of how to get this going? Because I'm sure there are many elements. It could be also like build tools also is a very compartmentalized way of doing things. And the JavaScript world is also has no shortage of variations appearing left, right, and center, and diverging ideas that then somehow have to come together as well. Do you have lessons learned that you've been doing this for 15 years or so that, okay, how do you do this? What is the catalyst that's needed? And just a quick win, I can understand it, but this means you're removing the vision of a baby of somebody, of a project that they started. How do you inspire that, and how do you fund it? Do you need to get grants? Do governments need to step in? Do you need to have more companies like QuantSight who are just willing to hire the people and give them that extra bandwidth to benefit? What's the way forward for this? I kind of struggle with this concept of it's super important. I think most people will recognize it, but will find convenient excuses not to execute. So what's the way forward? And if you had your golden wish, what would you tell the world to change?
This is a hard one. I think the answer to this question has like multiple parts. And I think the short answer is all of the above. You need governmental involvement. You need companies willing to fund this. You need grant bodies. And you need developers that are willing and able to take these kind of risks, especially when projects are in their infancy. I think there are several key things that really help with the success of, let's say, for the consortium in particular, which I'll talk for a moment on, is that QuantSight, because it's so deeply embedded in the scientific Python ecosystem, there's just a fundamental understanding of open source. The company just gets it. And also, it's central to its DNA. And that's what we put a lot of our emphasis and energy into supporting and sustaining. And for this particular initiative, QuantSight basically said, hey, there's a gap here. It needs to be filled. We need to get everyone in a room so they can start coordinating. How do we get this off the ground? And initially, we tried like a membership model in which companies had like an annual fee to be a part of, like you have different language bodies. And then over time, essentially, QuantSight was funding all the developer time on that to really push that effort forward.
Oh, and interesting.
That was a leap of faith and belief and willingness to eat the cost, because it was so fundamentally important, because they saw the business value and also saw what the potential was for it. And that risk only more recently has really started to pay off, where we're seeing the performance benefits, where we're seeing broader ecosystem alignment. And that that takes a little something. And so like hats off to the leadership at Quansight for kind of willing to buy into that. I also think that there are important initiatives within the grant space. So for example, your Chan Zuckerberg initiatives and your Sloan's and your Moore foundations, which at various points in time have said open source is pretty fundamental to the modern software ecosystem in the world and business applications. And so we need to invest in this. This is critical infrastructure. And that's the key, is you have to recognize it as infrastructure. And that kind of gets back into where governments have a role to play. And that's thinking about this in the same way that you have highways and bridges, et cetera. Like we're building the highways and bridges for the future. And I think there are certain key initiatives that are just now starting to happen. Like in the United States, there's a new grant program run by the NSF called the Pathways for Open Source Ecosystems, or the POSE grant. And this is entirely intended to take open source projects which are still in their infancy and giving them the resources to create communities around those projects. So you use that funding to set up test and build infrastructure, support tooling, to establish governance models, to do community outreach, maybe organize a small little conference, et cetera, to build momentum around it. And there's a substantial amount of money that's involved in that. It's a 2-year project of up to $1.5 million. You can do quite a bit with that. Yeah. And then there are other governments. For example, in the Netherlands, it's called NLnet Commons Fund, which is about making a whole bunch of small little bets about different open source projects and seeing which ones take off to establish the next generation of internet commons. I think these type of things, these are really critical in allowing projects like, for example, stdlib to get off the ground and actually be able to persevere for a bit longer to prove their value and worth. And hopefully at some point the spark catches and then it becomes a bit more self-sustaining. But it's a long path to get there. And so you need all these different funding bodies and companies, different stakeholders willing to help out and lift up at each step along that journey.
But it's interesting because it takes a while for people to see that. In the open source world, people say open source is free, it's great, right? I don't care who's doing it, but there's a small subset of people who put significant amounts of time, and it somehow feels that their reward function, if you will, is pure recognition. I'm always surprised when I go to conferences and talk to people about open source. It's actually very few people will actually ask, how does this whole system survive, work? Who's paying for this? Where is this money coming from? And people take it for granted. But it's important to understand how this whole thing is working. And once you understand the rules of the game, I think you're right. The word you said, infrastructure, and very quickly iterate that, oh, this is infrastructure. We put it in the infrastructure bucket, and now people say, okay, now money can flow. But not many people think of open source as infrastructure. So I'm glad you called that out. It's kind of an inspiring thing.
Yeah, I think the Ford Foundation at some point had a white paper or something like that where they use that. I'm pretty sure it was them. I could be misquoted, so take it with a grain of salt, but I'm pretty sure they use that exact language as well. I think there's like a recognition of just how fundamentally important software is to everything that we do. And it really is. It's the pipes, it's the highways for much of business operations, et cetera. And so you need that kind of massive investment. And people have been in positions of power, have been slow to recognize that. But I think we're starting to get that ship oriented in that direction. But to your point, yeah, a lot of the stuff that open source developers do is not necessarily visible to the naked eye. Like you don't really get a sense that your web browsers is running on a bunch of open source technologies, and people don't necessarily understand the incentives and why would people do this? You mean you're not going to sell this stuff? And they don't necessarily understand basically that software has a fundamental need and desire to be free just because of how people create and build these kind of things. If someone tries to monetize someone, eventually someone else is going to imitate that, do it for cheaper, then release it as open source, and that kind of wipes away your entire IP. I think we're building some education around this. I think there's a long way we need to go in terms of actually raising sufficient awareness, but I think books such as Working in Public do help advance that narrative. And I think hopefully in the future, we'll see increased commitment to really building this out and also sustaining people who really have a passion for building tools that have far-reaching consequences for all of us.
Do you have a favorite feature Do you have a favorite function that you've developed? Is there like one that is like closest to your heart that is, that of all the things I've done, puts the biggest smile on my face? Do you have something like that?
I do have a favorite one. You come from a language like MATLAB or Julia, or working with in Python, like you're familiar and have grown very accustomed to certain ergonomic syntax features, such as picking out slices of arrays and
the semicolon. Yes. Yeah.
Using the semicolon, like slice semantics, also doing like Boolean masking, all these kinds of things that allow you to do things in a few characters. And for various reasons in JavaScript, those syntactical niceties aren't immediately possible. And you end up having to, it's almost like you're having to write Java sometimes, where you just have like these really long call signatures, etc. And it just doesn't lend itself well to ergonomic development. And there was a recent addition, relatively recent addition. By recent, I mean like 2015, but to JavaScript to allow for proxying arrays and objects and intercepting some of the logic for property access. And building on this, one of the things that I recently implemented was all of the slice semantics that you would have in Python, as well as like Boolean masking and integer array indexing directly in JavaScript. So you have all those ergonomic benefits of slicing and dicing multidimensional arrays using syntax that looks almost identical to what you'd have in those other languages. And
are you serious? Does this exist?
Yeah. Yes.
So that just made my day. So I would have argued anyone who tells me about JavaScript, that would be probably one of my number one things is, how do I index into array?
Yeah.
It's not so elegant. You could say what you want. Not so elegant. So you've copied that syntactic approach. Is that it? And is that what you call your fancy indexing?
Yes.
You call it fancy indexing?
Exactly. We created like a fancy array container. So you can just, if you take like a normal JavaScript array, a built-in one, you can go array to fancy using our package. And then that gives you all these kind of like superpowers in which you can do arbitrary slicing. The only difference syntactically is that in, let's say, Python, you can do like A:B:C. You need to, you can do that exact thing. You just need to surround it by quotes. And then we take that string, do some parsing logic, resolve the slices, and then return different views. But we've also extended that to multidimensional arrays. So we provide an ND array container, just like in NumPy, that allows for working on arbitrary views of multidimensional data. Same thing, Boolean, integer array indexing, etc., using all that syntactical nicety.
So but is it complete? Is it a one-to-one mapping, or is it? There must be edge cases where you're struggling with, but how far is this?
So there's one area where I'm still writing the low-level implementation for doing Boolean and integer array indexing over multidimensional arrays. So it's there, but it's still a bit of a work in progress. Like we have some like slower logic that currently implements this, and I'm working on optimizing that and making it a bit more general. And I would hope that we'll have something that's basically feature complete one-to-one mapping within, the next few months. The entire behavior of NumPy style fancy indexing, we don't completely support yet, nor do I think that we will ever support. This is probably one of the learnings that I've benefited from being at Quantsite, is learning about all the mistakes or things that NumPy developers wish they had done differently. And one of them...
That no one else knows.
Yeah.
The best hidden secrets in the world.
Exactly. That's my competitive edge, is I have access to this knowledge that no one else really has, especially in the web ecosystem. And so I'm just as a sponge taking that all in. But one of the things is in MATLAB and in Julia, when you index into individual dimensions, essentially each of those indexing operations are orthogonal. You do like a Cartesian mapping. In NumPy, they do something called vectorized indexing, in which you zip together the indexes. Strictly speaking, it's more powerful, but it doesn't necessarily match user intuitions. And so that's probably something we won't replicate in standardlib. We'll probably go with like the Julia and MATLAB approach, and then provide some like functional utilities if you want to replicate what NumPy does. But more or less, I think we're well on the path to be able to have one-to-one mapping for most of the kind of common indexing patterns in JavaScript.
So I think that most of the listeners on this podcast come from the MATLAB, Python ecosystem, Julia, And there's a natural reluctance to think of JavaScript as a language, but you've obviously broken that myth in some shape or form. So do you have an example of something that most people are not aware of that actually is a good thing and that people just don't know and haven't bothered to figure out?
Yes, I think I'll answer this question with a little bit of history. So I think more people are becoming familiar with WebAssembly, which is a binary kind of compilation target for compiled language to run on the web. But before there was WebAssembly, there was something called ASM.js. And ASM.js was a project initiated by Mozilla, which asked the question whether they'd be able to define a strict subset of JavaScript to which statically compiled languages could be compiled and which was amenable to ahead-of-time optimization. And what they found is that not only could you define such a subset, but you could optimize that subset to achieve near-native performance. And this, to me, was a real eye-opener at the time and has influenced the way I write JavaScript ever since, as I realized that maybe I didn't need to immediately reach for C in order to squeeze out performance. I could just rely on JavaScript, and for most use cases, that would be fine. Of course, Julia folks will be listening to this and asking whether I've ever heard of Julia, which is another dynamically compiled language capable of basically native performance. That's all true. But Julia also has a distinct advantage of built-in types, and it also isn't the native language of the web, which was long derided as a very unserious language. You can get near native performance in JavaScript. And maybe that's like the larger point, is that I'm not sure how many people appreciate what an amazing piece of technology that web browsers are. And to me, it is a bit crazy to think that if you write JavaScript as if you were writing C with input values, having consistent types and using simple for loops and other constructs, that even though JavaScript is a dynamic, loosely typed programming language, JavaScript's engines are able to generate optimized kernels, which have more or less close to the same performance profile as if it was implemented in vanilla C. That, to me, is amazing. And also constantly sparks my curiosity when I'm writing a bit of code, measuring its performance and engaging in a bit of a Socratic dialogue with JavaScript engines and underlying compilers as to why and how something is being de-optimized, and thinking about the ways I can tweak my code to get it running with near native speed. And what's really great about this is that JavaScript execution engines are constantly improving in order to meet the ever-growing demands of web applications. And so there's just been an immense amount of energy and resources and time and effort by some of the brightest minds at these various companies and really trying to figure out how do you make JavaScript run fast. And that to me is when I realized that, I was like, no, JavaScript can be a really viable, easy to use, approachable framework for doing data intensive tasks. And with a whole new avenue of possible applications when you think about running in web browsers or in Node.js or other runtimes.
So just out of curiosity, so when you say it's getting faster, so I actually don't have that perception that it's getting faster. And maybe that's because things are getting heavier, and as a result, it feeds like actually it's getting slower, but actually there's much more. But how do you quantify that? How's that actually measured? I guess you could compare it to saying, yeah, if I boot up my MS-DOS back in the day, it was wicked fast. Yeah, today we're much slower. No, something's going wrong. But intuitively, it doesn't feel like that.
So you had to disentangle a couple things. There are a lot of ways you can make JavaScript slow, and there are a lot of foot guns. And if you write JavaScript in a certain way, in which you have like polymorphic interfaces and maybe variadic function invocations, you won't get optimized performance. You really have to have a mentality of writing your code like C. And that's where you have like dedicated interfaces for particular array types, or you're always providing numbers, or you need to wrap things in objects which always have the same shape. You can do things in JavaScript to where if you create objects or dictionaries and you create one object that has keys A and B, but then you create another object B and A in that order, and you provide those to the function, JavaScript compilers will treat that function as now no longer monomorphic, but it will consider it polymorphic. And so it'll create optimized kernels for those two different shapes. And as you do that, eventually you get into megamorphism, and then it goes into de-optimization hell, and you'll have poor performance in which JavaScript engines will dynamically interpret all the code that's being run. But if you always are very consistent about the shapes of objects that you're creating and passing in, then you get monomorphic optimized kernels, and that's where you get really the optimized C. Now, or the
Interesting you say this.
optimized behavior like C. And so that's possible. And that's a lot of the time I spent. Now there's an entirely different problem of web applications continuing to get more bigger and shipping down more and more code. And so the user experience may not always feel like things are quick and snappy because people are just bundling in a lot of stuff that either doesn't get used or it's not optimized correctly or just other things. And so there's the potential of JavaScript and what engine developers are working on, how they optimize code. And then there's like the reality of where we're still a long way from being able to fully take advantage of those capabilities. And that's probably where WebAssembly kind of circles back here. And what's nice about it is that in JavaScript, if you have a function and you're passing in a number and you get consistent performance, but as soon as you pass in like an object, now all of a sudden you'll get like a polymorphic function and your performance will decrease. And eventually you could get to a situation where you get really poor performance. So your performance profile isn't consistent.
Yeah.
With WebAssembly, you essentially get consistent performance all the time. So your baseline performance is already fast and it's never going to get slower. And that's one of the advantages I would say that WebAssembly has compared to JavaScript is that you can get consistent, good performance. That doesn't mean that JavaScript can't match that. You can, but you need to write your JavaScript very carefully in order to realize that.
So you bring up a very valid point because many people say MATLAB is slow. But if you go to folk who've been living and breathing MATLAB, they say, if you write MATLAB properly, it's actually really fast.
Yes.
And then you go to the Julia folk and Julia is really fast. But it turns out to get it really fast, it also takes a significant understanding of how to write the code in such a way it's there. And okay, so now you go to the Python ecosystem. The story's not that different. You can say, oh, Python is slow. Maybe if you write it slightly differently and you understand the libraries and the frameworks underneath it, you can actually get really good performance. So it's funny that you say you think JavaScript is slow, but it's not. You can get the performance. It just takes a bit of understanding. So
yeah,
it's not that different.
Yeah, you definitely need, it definitely helps to have a bit of an understanding of how JavaScript engines parse, interpret, and then try to optimize JavaScript code. Because once you understand a bit more the fundamental ideas of optimizing compilers and what the JIT is trying to do, that gives you insight in terms of how you need to structure how you write JavaScript. And that's why I keep coming back to, if you write it like C, you can get really great performance. And that's all informed by some knowledge about how most JavaScript engines work in terms of thinking about same shapes. They're often referred to as like hidden shapes, and how those things are interpreted and then used in inline caching, et cetera. And so if you have some of that knowledge, it goes a long way in allowing you to get the optimal performance. With Julia, yeah, same thing. And in MATLAB, yeah, of course, like arrange things in columns, not rows. With Python, Python in general, if you write things purely in Python, typically you don't get great performance. And we've run benchmarks where it's like orders of magnitude faster in JavaScript to do things. Python, the typical thing is if you want to go fast, you need to write in C, or you need to use Python, or you need to use Numba or something like that, some other external thing. But with languages like Julia and JavaScript, Julia is much farther down the path of the things that it can optimize. But in JavaScript, you can also do that same thing where you can get very good performance.
So I think part of the perks where you hear Python, it's not Python, it's wrappers around multiple languages.
Yeah.
So when a feature in the language improves, it's actually a very small subset. It can be a small subset of the ecosystem that benefits from that. The Julia ecosystem, I think they're mental slightly different, where the idea is that the more you write in Julia, then if the core language gets better, the ecosystem, you have an exponential improvement that is quantifiable across the board. And the idea is to write code so that you can mix and match different packages at a higher rate with multi-dispatch and so forth.
Yep.
But I'm also hearing from the JavaScript side, if you adopt the same philosophy, then actually the same thing can be achieved also in the JavaScript world. And that is actually a hidden gem that people probably don't think about. But it takes a while to see it. So thank you for reminding me this, because I often tell people, don't write Julia code as if it was MATLAB. Don't write it as if it was Python. It's a different language. You need to understand it. And you can do that for anyone. So I guess if anyone's listening that don't write JavaScript the way you write MATLAB, that's not the way to do it.
Exactly. Yeah. You need to have a little bit different mentality. But once you get in that mindset, the world's
Good
your
things
oyster.
to know.
There's a lot of powerful things you can do.
For people who want to learn more about you, the project you're involved, the company, what is the right way for people to reach out to you?
Yeah, the easiest way to find me is find me on GitHub, because that's where I basically live most of my life. But people can also reach out to me personally over LinkedIn. You can just search for Athan Rains. Quansite, you go to quansite.com. We have a blog. We're always pushing new updates in terms of what we're working on and some of the more recent ecosystem developments, especially how we're advancing scientific computation within the Python ecosystem. So yeah, you can find me online. And if you want to get more involved, at least in standardlib, we have a set of contributing guides and development guides to help people get started.
So what's the right way? So let's say I'm curious about this, right? So let's say I've got a technical computing background, but I know very little about JavaScript, and my inner voice says, JavaScript's not the right language. What do you tell those folks to get involved? And is there a path where you can slowly but surely start with small things and it's okay to contribute? What would be your recommendation for these folks?
I would say if you know a little bit of C, you can write some JavaScript. And that's essentially what we do. We write JavaScript as if we write C. A lot of the stuff, we're not just doing stuff in JavaScript. We're writing things in C and Fortran. We're creating bindings. So if you have numerical computing expertise or experience, or you've worked with BLAST and LAPACK, there's definitely various places you can slot in on the work that we're doing at standardlib. And any gaps that people might have, we're happy to fill those in. It's like a startup, is that the people who are best equipped to build the thing aren't necessarily the best equipped to scale the thing. And you need a really diverse collection of contributors and other people within your community who bring different skill sets and talents to really make a vibrant and successful and sustainable project, one that can scale to different users. You need designers to come and help you build cool websites and make it visually appealing and work in different environments. You need people that are good technical writers. You need people that can write engaging and captivating blog posts, but you also need people that have comfort and familiarity with working with low-level numerics. And it's hard to be all of those things at once. And honestly, one of our biggest gaps is marketing and publicity and showcasing a lot of what we've built, because we've built a lot of really cool technology. But at the same time, that's not necessarily, for example, my core expertise. I would love to just be spending my day writing low-level kernels. And while I can come up for air and write some blog posts, there's only so much time in a day.
Draw your energy.
So you have to pick and choose. And I think historically we've really prioritized the technical development, and now it's becoming more and more imperative that we need to invest a lot more time and energy into kind of raising the profile, creating a lot of content, tutorials, workshops, etc. And I think that's the key gap or area which these grants, such as the NSF POSE grant, which is about creating these open source ecosystems, can really drive change and really help projects scale, because it gives projects the resources to hire technical writers, contributor experience leads, people that are good at creating marketing content to really help build momentum and create a community around these projects.
That's it for today's episode. I hope you enjoyed the conversation and found it valuable. If you did, please consider sharing this episode with your friends and family, or anyone who might benefit from it. Also, I'd love to hear your thoughts, so take a moment to leave a review and let me know what you think. And if you haven't already, don't forget to give us a rating. It really helps us reach more people and bring you even more amazing content. Thanks for tuning in, and I'll catch you on the next episode.